Today we are going to be starting another chapter, Chapter 9. Title of Chapter 9 is Chemical Bonding Part 1, the Covalent Bonds. Just so you know, Chapter 10, obviously the chapter after this, is Chemical Bonding Part 2 of the Covalent Bond. We'll be doing this normally in class, we'll be doing Chapter 9 and 10 together as one chapter, almost like a one chapter test. And it's the only chapters we would be doing together at the same time. Okay, but being online doesn't really matter. So first of all, one of the big things about this chapter, chapter 9, is something you may have done before, and it's something called Lewis dot structures. If you have done it before, then half of, not all, but half of chapter 9 will be a bit of a review. And if you've never done it before, it's not that bad. It's just kind of like balancing equations. If you've never done it before, it's not bad. Just takes a bit of practice. In cases like I'm not sure if I've ever done one. This picture here, the stamp here, is a picture of a slightly complicated Lewis dot structure. We will not be doing Lewis dot structures that are this complicated, but it's a Lewis dot structure either way. What does a Lewis dot structure even show us? It shows us what atoms are bonded in a molecule and how. Not only is it what makes it up, this is a Lewis dot structure of a molecule called benzene. You don't need to know what that is right now, but I'm just telling you this is benzene. Benzene is C6H6, which is 6 carbons, and if you count, there are 6 hydrogens. 6 carbons and 6 hydrogens. You can write benzene as C6H6, but written down, okay, all you know is there's 6 carbons, 6 hydrogens. But how are they bonded to each other? How are they connected? This is how they're connected. Again, we will not be doing Lewis dot structures like this in this chapter, but this is, again, a more complicated one. But it tells us that every carbon in this, according to this picture, is connected to 2 other carbons, and each carbon is connected to 1 hydrogen. There are single bonds and double bonds in it, if you know what those mean. If not, that's part of the chapter. So this picture here is a Lewis dot structure. It shows us how things are connected. It's kind of like almost like saying if you had 6 red Legos and 6 yellow Lego pieces. Okay, you know, and you connect it somehow. You know there are 6 yellow ones, you have 6 red ones, but how are they connected? So that's kind of what a Lewis dot structure tells us. Not just that there are 6 red ones, 6 yellow ones, but how they are connected. So that's in general, what a Lewis dot structure. A little bit more, there's more details about it, but in general, that's kind of how it works. Okay, Lewis dot structures. So before we get to Lewis dot structures, there's some terms we have to know. Starting the first one, if this thing will work. There we go. Valence electrons. This came up in the last chapter, but valence electrons, they're outer shell electrons in an atom. The valence electrons are the electrons that are participating in a chemical bond. So valence electrons are the outer electrons, and they're the ones that are bonding. So how many electrons are there? Well, it depends on what group they are in the periodic table. In this chapter, we are only going to be talking about representative elements. Representative elements are, the main body elements on a periodic table, not the transition metals though. Okay, so this does not include transition metals. What we know is group 1 on the periodic table. Okay, I don't have a periodic table in front of me right now, but group 1 on the periodic table, all end in something S1. There is 1 outer electron or 1 valence electron. The outer electrons, that's something S1, that 1 outer electron is your valence electrons. Group 2 elements all end in something S2. The outer shell of electrons is 2. There are 2 valence electrons. Group 3 elements, 3A elements, all end in something S2, something P1. So 2 plus 1 or 3 outer electrons. Group 4 elements have 4 outer electrons. You can see a pattern here. Group 5A elements have 5 valence electrons. The reason why group 5A elements are something S2, something P3. 2 plus 3 is 5. Group 6 elements have 2 plus 4, which is 6. And group 7A has 2 plus 5, which is 7 valence electrons. Not written on here, but group A elements, 8A elements have 8, with one exception. We'll get to that later. Okay, so those outer electrons, also known as the valence electrons, are represented as dots. They are called Lewis dots. Group 1A, 2A, remember 3A, we're not including transition metals. Group 3A starts here, 3A, 4, 5, 6, 7, 8A. Group 1 has 1 valence electrons. They will be represented by 1 dot. Group 2 has 2 valence electrons. They'll be represented 2 dots, 3 dots, 4, 5, 6, 7, 8. The exception to that is helium. Helium only needs 2 because there is no 1p level. That's the reason why. We're only going to do representative elements or noble gases, but definitely we don't include transition metals into this. So, one other thing, some people usually come up, ask in class, like, hey, those 2 dots, one on left to right, should they both be on top or on bottom or left or right? It doesn't really matter, as long as there's 2 dots total. Group 3, 3 dots total. So some of you might have learned, hey, I'm supposed to put 2 on the left, 2 on the right together for a total of 4. As long as there's 4 total, that's the main thing. It doesn't totally matter if you want to put, 2 on the left, 2 on the right, or 2 on top and 2 on bottom, like pair them up. Though we'll see later on that electrons usually do come in pairs. But for now, in general, as long as group 4 has 4 dots, group 5 has 5 dots, group 6 has 6 dots, it's all good for now. Okay, so these things are called Lewis dots, and they represent the valence electrons. Lewis dots represents the valence electrons. Okay, let's start with some ionic compounds, ionic bonds. The compound lithium fluoride. Lithium is group 1. How do I know? Right here, lithium, group 1. Fluorine, by the way, group 7, 7 dots, since it's going to come up in a second. Fluorine, 7 dots. By the way, that picture is lithium fluoride. Lithium, group 1, fluorine, group 7. I know because on the periodic table, group 1, group 7. When they combine together, they make a compound lithium fluoride. Lithium loses an electron, becomes positive. Fluorine gains electron to become negative. Now, why is that? Why would lithium lose an electron, fluorine gain electron? Well, the electron configuration of lithium is this: 1s2, 2s1. That is regular lithium. Regular lithium is right here, 1s2. This is the 2s level, 2s1. If it loses an electron, then instead of, so if lithium loses an electron to become positive, which electron does it lose? It'll lose that 2s1. It's going to lose that 2s1 to just be 1s2. So if this thing loses an electron, it'll be just 1s2. What is that, the term isoelectronic? What is that isoelectronic? What neutral atom is isoelectronic with? Meaning what element has electron configuration 1s2? Looking at periodic table, what element is 1s2? It's helium. That thing would be helium. So 1s2 is the same as helium. And we know helium's electron configuration, noble gases, are very stable. Let's get fluorine. Fluorine is regular electron configuration is 1s2, 2s2, 2p5. That's normal fluorine. If it gains electron, it'll be negative. This is regular fluorine, this is fluoride ion, gains electron. And so if you gain an electron, instead of it being p5, it'll end up as p6. What element is this isoelectronic with? What ends in 2p6? Going back to the periodic table, hold on. What ends in 2p6? Again, 2p1, 2p2, 2p3, 2p4, 2p5. Neon ends in 2p6. The noble gas neon ends in 2p6. So what is that the same as? That's the same as neon. That's the electronic configuration of neon. So lithium loses electron to be like the noble gas helium. Fluorine gains electron to be like the noble gas neon. And once they have a noble gas electron configuration, they're stable. So in ionic compounds, in this case lithium, it loses electron, and fluorine will gain electron. One is positive, positive lithium, one is negative, negative fluorine, and the two charges attract. Opposite charges attract. And that's what this picture is of lithium fluoride. There's a lot of ionic compounds like that. The most common one is salt. Okay. So, and of course, way back in chapter 2, ionic compounds in general, metals and nonmetals. Oh, in fact, that's what that is. Lithium metal, fluorine nonmetal. How do I know again? Ooh, let's get periodic table. Remember, there's a staircase thing on the periodic table. The left side of the staircase is metal. The right side, or the upper right side of the periodic table, non-metal. Lithium's a metal. On the other side of the periodic table, fluorine is a non-metal. In general, metals and non-metals are ionic. Sodium chloride, the most common ionic compound that we know. Where is it used a lot? In something called chloroalkali process to make chlorine, sodium hydroxide, sodium hydrogen. Why in the world do we need to make that stuff? Why do we mine salt? To make these compounds. Where will we use chlorine, sodium hydroxide? For stuff like cleaning. Okay, just think like Clorox soaps. So lots of these things are used, sodium chlorides are used to make other compounds. These are like the ingredients to make other things. We do use it to melt ice on roads, not in Los Angeles, but you know, other parts of the country where it's freezing, almost never in Los Angeles. And of course for other process, meat process, food canning, water softening, etc., etc. But all the salt that we use for actual food, for human food, not that much. Domestic table salt, 3% of all the salt that we either evaporate from ocean for sea salt, or mine for salt. Very little of it, or I shouldn't say little, it's about 3%. It's actually used for human consumption. Or actually not even, it's just, you know, like cooking, whatever. Most of it's used for industrial purposes or melting ice on roads. Glad I don't have to live in that. Okay, going on. So that's ionic compounds. Then there is covalent. Covalent compounds is when two atoms, a chemical bond when two or more electrons are being shared by two atoms. Two atoms share electrons. Again, some of this stuff might be a review for some of you guys, and that's fine. And so remember, the most stable atoms are the ones where they have eight valence electrons, 8 outer electrons. And so fluorine, we said, was group 7. Why would, say, fluorine and another fluorine want to share electrons? The most stable form is if they had 8, or in a way 0, outer electrons. So if this one gave an electron to the other, one would have 8, but the other one would have 6. Okay, either way, if one lost it, the other one gains it. Okay, if something loses, it's conservation of mass. If something loses it, it has to be gained somewhere. But so in these two atoms, why would they share electrons? Well, if one has 8, the other one has 6. And therefore, it would never be stable. But what happens instead of one gaining one losing one is in fluorine, they're going to share electrons. So that's, okay, both of them group 7. They're shared electrons. It's almost like a Venn diagram. They're share that pair of electrons in the middle. They're share that pair of electrons in the middle. So this fluorine has 2, 4, 6, 8 electrons. The fluorine right has 2, 4, 6, 8 electrons. They both have 8 outer electrons, and that is what a covalent bond is. That they both have 8 valence electrons. After this, I'm going to do, or after this specific video, I'm going to record using camera a bunch of other Lewis dot structures. But them sharing electrons, that is a covalent bond. Usually we represent the shared pair of electrons with a single line. This single line represents that pair of electrons right there being shared. It's also known as a single covalent bond. Oops. Let's start with that. Single covalent bonds. The unshared electrons, okay, so single covalent bond, that pair of electrons being shared. The unshared electrons, which is what those were, are known as the lone pairs. So the unshared electrons are, by the way, they're always called lone pairs, never lone singles. Okay, so lone pairs are always going to be 2s. A lone pair there, lone pair there, lone pair there. Okay, the shared electrons, that shared pair of electrons, is called a single covalent bond. We'll get to, yes, there can be a double bond, not yet. Okay, hold on, we're getting there. So the shared pair of electrons is a single covalent bond. The unshared electrons, the ones that are just there, are called the lone pairs. The lone pairs in this chapter, for right now, they're there. Please include them. They're going to be important, especially later on. Okay, later on in this chapter as well as the next chapter. But for now, they're there. They're lone pairs of electrons, and just make sure that you leave them in there. Okay, so the unshared or the shared electrons, this line, every line represents 2 electrons. So this fluorine on the left has 2, 4, 6, 8 electrons. The fluorine on the right has 2, 4, 6, 8 electrons. That's the Lewis dot structure. Okay, and I think we're going to pause for now. I'm going to do some other ones on using my camera. It's just easier to do a bunch of examples on paper.